Okay, good evening, everyone. Welcome to the live session for week 6. So, this is the course Industrial Wastewater Treatment, and I'm Nikita. I'm a PhD student from IIT Madras, and I will be the live session PA for the course. So, what we will do here is we will discuss some basic topics that you must have seen from this week's lectures, and then we will solve some numerical problems. So, if you all have any doubts from this week's lectures, then let me know. You can ask now. So, if there are no doubts, then we can proceed with the class. So, any doubts, any of you? My screen is visible to all of you. Okay, so I see no questions. So I will start with this week's lectures. Uh, so, so in this week you must have seen about sludge, how sludge is treated, how it is disposed and handled. So, and you must have also seen how to design sludge drying beds and so on. So we'll focus on that now. So let's start with sludge. So what is sludge? What is sludge? No answers? So sludge is settled solids generated during wastewater treatment. And you must have seen like how we have primary sedimentation tanks, secondary sedimentation tanks. So what do all these do? They collect all the settleable solids. So in primary sedimentation tank, it is used for mainly collecting the colloidal solids. So after undergoing coagulation and flocculation, the flocks will settle down in the primary sedimentation tank. And then after biological treatment, whatever biomass is left, so that will be settled in the secondary sedimentation tank. So the solids which are collected from these two tanks will be called as sludge. So sludge is nothing but solid. It is mostly solid. It is mostly liquid actually. So the percentage of solids in sludge is about 1 to 4%, which is significantly higher than what is there in the inlet wastewater. So 1 to 4% solids, and the remaining is water. And there are different types of sludge, like I just told you. we collect sludge from primary sedimentation. We also collect it from secondary sedimentation, and based on that, we can classify into different types. The first one being primary sludge. So, what is primary sludge? Any guesses? Any ideas? It's okay even if your answers are wrong. So we are all here to learn, so it's fine.
Any solid or organic components.
Sorry, can you repeat? Organic components. So primary sludge is the sludge.
Organic and inorganic component and solids.
So primary sludge is the sludge which is generated from primary sedimentation tanks. So and we use primary sedimentation tank for coagulation and flocculation for settling flocks. So whatever flocks are collected, those will be called as primary sludge. So primary sludge is usually it is grey and slimy, and it also has an offensive odor. So because it is like untreated, it still has to undergo biodegradation. It is not biodegraded. That is why it is not very stable and it quickly decomposes. So that's why it has a very offensive odor, and it also appears very grey and it's like a jelly. So that is primary sludge. And then we have chemical sludge. So chemical sludge comes from like what we discussed last week, right? We saw how precipitation is used for removing heavy metals, and we also saw about coagulation and flocculation. So chemical sludge is basically that which is generated from precipitation. So the decomposition of chemical sludge is slower because chemicals are added. So these chemicals can be harmful for the bacterial growth, so they don't decompose as quickly as primary sludge. So chemical sludge, some precipitant chemicals are added. That is why it is called so. And then there is secondary sludge. So what is secondary sludge? It's very simple, right? If primary sludge comes from primary settling tank, then where will secondary sludge come from? Answers?
It comes from secondary treatment.
Right, correct. So it comes from secondary sedimentation tanks or so secondary sedimentation tank, it goes to the tank after being biologically treated. So once it goes through activated sludge process or ASP. So activated sludge process is where we allow the bacteria to grow and decompose the organics present in water, all the while stirring the reactor continuously and aerating it. So aeration is provided so that the bacteria can grow and digest the organic matter. So the sludge that comes from ASP is allowed to settle in a sedimentation tank. So that is your secondary sedimentation tank. And usually the sludge coming from here is odorless. Reason being, all like most of it is already degraded and stable. So if it was unstable, then there will be some odor. But because it is already degraded, and that is why it is odorless, and it is also readily digestible. So since it is partially digested sludge, sometimes even fully digested, so partially digested sludge will be there. So that can be further degraded. If we are going for aerobic processes, then it will be done very quickly because it is already partially digested. And then we have trickling filter sludge. So, can someone tell me what is trickling filter?
Trickling filter is biological wastewater treatment system.
Yeah, but what is the difference
Fixed way,
between?
fix, like fixed way.
Yeah, correct. So it is a fixed type of system. So in activated sludge process, the bacteria remains suspended, but in a trickling filter, the bacteria is fixed. It is fixed to a surface. So it is like so there are discs like this. So wastewater will be flowing from the top. So wastewater will flow and bacteria will be on the surface here. So as wastewater flows through, it will come and it will go to the next filter and it will flow like this. So because it trickles down, it's called a trickling filter. And as it passes through each of these filters, it's the bacteria on the surface of the bacteria present here will degrade the wastewater, organics present in the wastewater as it passes through each of these. So that is the difference between ASP and a trickling filter. In ASP, we will have bacteria in suspension, but here it is fixed to a surface. So this is a fixed growth or attached growth system, whereas in ASP, it is a suspended growth system. And yeah, trickling filter, mostly what happens is when we have wastewater which is flowing. So because of the velocity, as wastewater flows, the bacteria will digest the organics and sludge will collect at the top of this surface. So this sludge is nothing but dead bacterial cells and some organics which make up the surface. So once it becomes very thick, because of gravity and the flow of wastewater from the top, the thick layer will fall down. So it will fall down and it will be collected at the bottom as sludge. So whatever sludge was there, it will sloughen. This process is called sloughing, and it will fall down and it will be collected at the bottom. So this sludge is called trickling filter sludge. So in case there are plants having trickling filter, so this sludge is called as trickling filter sludge. And another major difference between ASP and trickling filter is that in ASP it is a closed. It's not closed, but it's like everything is contained inside. So this is the tank in which you have bacteria suspended, and the bacteria will react, and stirring is provided, and there is also sufficient air bubbling or aeration. So all this happens. But in case of trickling filter, it's out in the open. So because this structure is like it's not enclosed on all three sides, it is open to attack by flies. So what flies do is they lay their larvae. So they lay their eggs and the eggs hatch and they become larvae, and then there could be some worms also. So all these insects can get into the trickling filter and they can continue growing there. So the sludge coming from the trickling filter can have all of these. So that's the difference between sludge from ASP and sludge from trickling filter. In trickling filter sludge, we also have some insects along with the biomass. And also, the sludge from trickling filter can be having an offensive odor because it rapidly decomposes. So because there are also insects like flies and all, so that's why there could be some odor. And then the fifth one is digested sludge. So sludge digestion is done after collecting the sludge, and once digestion is complete, then it becomes more stable. So, and once it is stable, there is no odor. And it is also easy to dry and dewater. So we look at all these processes, but sludge digestion is done in two ways. First is using aerobic processes, and second is using anaerobic processes. So there are two different ways. So all of this you must have seen in this week's lectures. Now coming to a very important property of sludge, which is the moisture content. So can someone tell me what is moisture content or water content? What is moisture content or water content? What is the formula? So moisture content, as the name suggests, is how much water or moisture we have in sludge. So the formula for this is moisture content equals weight of water by weight of the total sludge. So like I said before, sludge has 1 to 4% solids. So if let's say it is around 3% solids content, then what will be the water content? Imagine you have 100 grams of sludge and you have only 3% of solids. So what will be the you have only 3% solids. So 3% of 100 grams means 3 grams, right? So out of 100 grams, if 3 grams is solid, so how much of it is water? So if 3 grams out of 100 is solids, then we are left with only 97 grams, which is water content or the weight of water. So it is 97 grams. So the total is 100 grams. So moisture content is about 97%. So this is just an example that I'm giving. So it's not like a standard value or something. Okay, and there are different types of water in sludge. First one is free water. So what is free water? What is free water? So free water is water that can be separated using gravitational settling. So this means we just allow the sludge to, we just allow the water to settle down and we can collect it, or we can just put it on maybe like a sieve or something, and the water can pass through the sieve and then it can be collected. So we don't need to apply any pressure or anything. So that's free water. So this will occupy some 70 to 75% of the sludge volume. So that's free water. And then we have interstitial water. So interstitial water means water that is contained in the interstices or voids. So like sludge particles can be having pores or voids. So this area, this is a pore. So imagine there are other particles also nearby. So this shaded area is the pore area. So water that is collected in this area is called interstitial water, and this can also be the water which is trapped inside flocks. So for example, we have a flock. So maybe the flock is jelly, and on this we have a layer of water. So the water inside the flock is also called interstitial water. And there are bacterial cells. So bacterial cells bacterial cells will have some protoplasm inside, and this also contains water. So the cell structures of bacteria, the water present inside them, is also also comes under interstitial water. And this constitutes about 20% of the volume of sludge. And then we have vicinal water. So this is water which is held due to the particle surfaces. So if the particle surface is uneven, like it's like there are some voids or there are some like rough surfaces like this. So the water can hold on to the crevices here. And if there are like 2-3 particles adjoining, then this becomes held by 2 particles together. So this is vicinal water. So because of the shape of the particles and because of the molecular structure of the particles, some water will be held. So that is vicinal water. And then there is water of hydration. So water of hydration means like generally any organic substance will be composed of carbon, hydrogen, oxygen, nitrogen, sulfur. So because these are organic compounds, mostly it will be composed of carbon, hydrogen, and oxygen also. So when these organic substances they decompose, they release water. So this water is chemically bound water, and it is removed using thermochemical processes. So sometimes the water will be held chemically. That is, there will be some chemical bonds so which cannot be removed using physical means. So we need some thermochemical processes for their removal. Okay, so now coming to the specific gravity of total solids. So before that, what are total solids? Total solids means sum of fixed solids and volatile solids. And to determine the specific gravity of total solids, we use this formula, which is WSL by SSL plus WS by SS. So here WSL is the weight of solids plus weight of water, and WW is the weight of water. WS is the weight of sludge solids or weight of dry solids. SS is the specific gravity. Of sludge solids. SW is the specific gravity of water. This SSL is the specific gravity of sludge. Now here volume of sludge VSL becomes equal to WS by rho W into SSL into PS. So if you want to find the volume of sludge, you have to use this formula. So WS, as indicated here, it's the weight of dry solids. Rho W is the weight, density of water. SSL is the specific gravity of the sludge. And PS is the percentage of sludge solids. So PS is the percentage of sludge solids. So like I said previously, it is about 1 to 4%. So we have to assume accordingly. And then we have a parameter called the sludge volume index. So this is supposed to be a live interaction session, so you are also expected to participate in the lecture, and also if you have any doubts or questions, or if you have something to say, you are always welcome to say, and you are also expected to answer if there is a question. So if there is no interaction, then it's not a live session, right? So what is sludge volume index? So what is sludge volume index? So it is a parameter of sludge, and it is measured using a device called an Imhoff cone. Now this cone here will be filled. Sludge will be added to this, and it will be allowed to settle for a while, for about 30 minutes. So if you allow the sludge to settle for 30 minutes, what happens is all the solids will occupy at the bottom, and anything that does not weigh, anything which is light, and even water will occupy the top portion. So then we find out how much volume. So usually this cone is graduated, so you can see how much ml are occupied by the solids at the bottom. So the sludge volume index is the volume occupied by 1 gram of activated sludge settled in the Imhoff cone for 30 minutes. So for this you need the weight of the sludge that is settled, and volume you can calculate from here. You can take the reading here. So this will tell you volume. So sludge volume index is the volume occupied by one gram of sludge which is settled in the Imhoff cone after 30 minutes. So if you want to find out the sludge volume index, then you have to find how much volume there is. You have to multiply that with 1000 and then divide it by the mixed liquor suspended solids, or MLSS. Now, can someone tell me what is MLSS? Have you come across this term before? Do you know what it means? You can share so that even other people can learn from you.
Mix of suspended solid.
Yes. Mixed liquor suspended solids. What does it mean? So mixed liquor suspended solids, or MLSS in short. This refers to any microbes or bacteria which is present. So it mainly denotes the bacteria which is dead or alive, which comes along with the sludge. So that is your mixed liquor suspended solids. And SVI equals volume of sludge into 1000 divided by your mixed liquor suspended solids. Because it is assumed that most of the sludge is mostly bacterial cells, mostly dead bacterial cells. And the unit of sludge volume index is milliliters per gram, because volume we have at the top, and MLSS we usually give it in kg or grams. So yeah. And then we have another parameter called sludge age. So sludge age is like, it is also called mean cell residence time. So MCRT for short. So it is the average number of days the solids or bacteria remain in the system. So, um, so it's like the lifetime of the bacteria, or like if it is like how many days the bacteria will remain inside the tank, degrading the pollutant. So its lifetime is, or either if it is, it can. I mean, if it's a short-lived bacteria, then of course it's its lifetime. But if the process is very quick, then it is the time until which the process takes place. So either of the two. So basically, it is the time for which the bacteria is going to live and react and digest the sludge inside the tank. And once it is out of the tank, then that's it. We don't consider the time after that. So it is the average number of days the solids or the bacteria with remaining inside the system. And then we look at sludge management. So we already saw a bit of this in the previous class when we talked about precipitation, etc. So the first step in managing sludge is thickening the sludge. So what is done in sludge thickening? What is sludge thickening? What is done in this process? So sludge thickening is basically volume reduction and concentration of the sludge. So basically we are trying to concentrate the sludge to increase the solids ratio, and at the same time we are trying to reduce the amount of water. So if we reduce the amount of water, obviously the volume of the sludge also will reduce. So why do we do this? We do this to help with handling and for also aiding further treatment. So handling, like if it is very bulky and if it is if there's a lot of water, then it's going to be difficult to treat the sludge because we need to design all the treatment systems accordingly. So that's why if we try to reduce the volume, then we can also reduce the cost of installing these systems, and we can also make the systems run more efficiently. So yeah, that's why we need sludge thickening. So how is it done? There are like many methods available for this. So one of them is gravity thickening, then centrifuge thickening, and flotation, belt thickening, and rotary drum thickeners. So flotation based thickening is based on density difference. So if it is if something is less denser than water, then it will float. So what we do here is we aerate the sludge along with water so that along with the air bubbles will stick to the sludge particles and it will help the sludge float on water. So that is flotation thickening. And gravity based thickening is we just allow the sludge to be we just allow the sludge to settle, and over time whatever solids are there they will come to the bottom, leaving water at the top. So that is gravity based thickening. And then we also have centrifuge thickening where we use centrifugal force. And then belt thickeners. So belt thickeners are like rotating here. So over the belt we will have some absorbent material which will absorb water, and the sludge will be allowed to pass through here. So this will be the inlet, and from this the sludge will pass through, and as it passes through the belt water will be absorbed and it will be collected at the bottom. And then the next process is digestion. So the first technique is through biological means. So biological digestion can be aerobic, or it can also be anaerobic. So I think by now you must have already known what the difference between aerobic and anaerobic is, so I'm not going to go into detail. And then we have heat treatment. So it is simply applying a high temperature so that the organics get decomposed and we are left with something which is stable and which is a mineral product. And then we go for wet oxidation. So this we oxidize mainly the organics or the organic component of the sludge using this. Once we are done with digestion, we go with dewatering. So again, even after the digestion process, there will still be water in the sludge which needs to be removed. So why it is done is because we need to prepare the sludge for the next step. So in the next step is disposal. So before disposal, we have to ensure that there is no moisture left out. So for this, we do dewatering, and dewatering is done using drying beds. So, and then also using a device called a filter press. So this basically some external force will be applied on the sludge, and whatever water is left in the sludge, it will be filtered out. So that's your filter press. And then the final step is disposal. So disposal can be done through incineration. So if incineration is opted, then it is best to ensure that there is no moisture left. So that is why in such cases the dewatering step becomes very important, because if we have any moisture left, then there won't be any it's not possible to incinerate something which has moisture, right? There won't be any burning. So if we are going for incineration, it's always better to dewater the sludge properly. And the second step is land disposal. So just whatever the watered sludge is there, we are just going to put it in the landfill and dispose it. And then soil conditioning. So especially if we have any agricultural farmlands, then these sludge can be used as manure or soil conditioners. So they help water percolate in the soil in a better way. And then there is ocean disposal. So this is very clear. So directly dumping the sludge into the ocean after dewatering, and then underground disposal. So underground disposal is excavating the soil and then putting the sludge inside. So we can have like a storage room underground, so where we can store the sludge. One second. Hello. Hello. நீங்க எங்க இருக்கீங்க? கோவிலுக்கு எதிர்க்கதாங்க. கோவில் பக்கத்துல ராஜநாயக்கர் ஹாஸ்பிட்டல் இருக்கா? அதுக்கு எதிர் வீடுதான். கற்பகாம்பா ஃபவுண்டேஷன். ஆ? கற்பகாம்பா ஃபவுண்டேஷன் கோவில்ல இருந்து ரைட்டு. இல்லங்க, இப்ப கோவில் முன்னாடி நீங்க நிக்கிறீங்கன்னா ரைட்டு திரும்பி. ஆமா ஆமா. Yeah, I'm really sorry. So let's get back. So underground disposal means like having an underground facility like a storage room where we can dispose the sludge. And then we have another important property called the solid loading rate. So it is also called SLR in short. So this solids loading rate is the amount of solids loaded per unit area per unit time. So this is similar to the liquid loading rate that you would have seen in sedimentation tanks. So or the hydraulic loading rate. So solid loading rate is very similar to it. So instead of water, here we will be seeing how much mass of solids are entering or loaded per unit area of the digester per unit time. So the units accordingly will be solids are expressed in kilograms and area of digester will be in meter square and time is usually in hours. So can you tell me what will be the units for SLR? What are the units of solid loading rate? What are the units of solid loading rate? I just told you, right? It is kilogram per meter square per hour. Am I not audible, or you're not able to follow my lecture, whatever I'm saying? Or see, if there is any issue from my side, you can let me know. So, okay. Now we'll be looking at factors influencing sludge digestion. See, if you don't want to answer, then you can even post it, like you can post a message also. So that's fine. You don't have to switch on your speaker and then talk. You can even put a message. So there are different factors which are influencing sludge digestion. So the first one being temperature. And temperature is important because if we increase the temperature, then the rate of digestion will also increase. And there are different bacteria which are operating at different temperatures. First, we have the mesophilic bacteria, and mesophilic bacteria will operate in the range of 25 to 40 degrees Celsius, and the optimum temperature is 35 degrees for this. And then we have thermophilic bacteria. Thermophilic bacteria operate between 40 to 60 degrees Celsius and optimally at 52 degrees Celsius. And the next factor is pH. So the optimum pH for the sludge digestion process is between 7.2 to 7.4, which is close to neutral. And then how much seeding we give. So what is seeding? What do we mean by seeding? Why is it done? Is my voice clear? Am I audible?
Yes, ma'am.
Yeah. So what is seeding? Can I get some answers? What is seeding?
Biological degradation.
Seeding helps with biological degradation. So what happens is, like, in biological degradation, the bacteria will degrade the organic matter, right? But we have to, in some cases, the bacteria will not be able to grow, or if there is like very less bacteria, then it won't be enough. Or there might be some chemicals which harm the bacteria, and the bacteria will not be able to grow. So, in those cases, seeding will introduce the enzymes which are necessary for the bacterial growth. So if we introduce enzymes plus bacteria, then that is called seeding. So this will introduce the bacteria to the sludge, and also it will have enzymes which will help the bacteria grow. So what happens if bacteria grow? There will be proper digestion, and the rate of digestion will increase. And then the fourth factor is mixing and stirring. So mixing and stirring will improve the rate of digestion. So the reason being, like if you don't mix and the reaction is going to happen only at one part, so it won't be uniform. Only if you mix sludge or if you give a proper stir, only then the reaction rate will be uniform across the tank. Otherwise, what happens is it will be concentrated at one portion. So maybe somewhere here, and then in some places the reaction will be more, and in other places there won't be any digestion taking place at all. So, in order to achieve uniform growth of bacteria and uniform rate of digestion, it is important to keep mixing and stirring the system. And when it comes to aerobic digestion, mixing and stirring also helps supply oxygen to the system. Okay, now looking at the types of digestion. First one is aerobic digestion. So aerobic digestion is done in smaller plants. So in aerobic digestion, the bacteria consume their own protoplasm, meaning they go into a stage of autophagy where this happens especially when there is less organics present. So organic matter is the food for bacteria, and in case the food goes less, then what they do is they consume their own protoplasm. And there is even a specialized type of aerobic digester called autothermal thermophilic aerobic digester. ATAD in short. So this operates at higher temperature because it is thermophilic. So it operates at 45 to 70 degrees Celsius. And in this, the sludge becomes pasteurized. Pasteurized meaning all the bacteria and harmful microorganisms are killed. So the sludge is clean. But aerobic digestion is expensive because we need oxygen supply, and we also need to mix the keep mixing it continuously. And also the aerobically digested sludge has poor dewatering. So we've already seen how to do dewatering. We discussed various methods available. So aerobic digested sludge will not dewater properly, meaning it won't be able to release the water that it contains. So in that case, it won't be useful to take it for incineration, because for incineration we want complete dewatered sludge. There should be minimal moisture. But in case the sludge is not able to release water properly, then it becomes unfeasible, right? So that's why aerobic digestion is not preferred. So in most cases, anaerobic digestion is done. So in most wastewater treatment plants, anaerobic digestion is preferred. So anaerobic digestion has different phases. or steps. So the first step is hydrolysis. So in hydrolysis, whatever complex compounds are there, complex organic compounds, they are converted into soluble, simple solubilized compounds. So, for example, you have cells. So, cells are organic matter and they will be converted to water, carbon dioxide, sulfur dioxide, maybe nitrates and nitrites. So, all of this happens in hydrolysis. So, in the presence of water. And the next step is acidogenesis. Uh, like it can also be converted into like if the organic compounds contain any fatty substance or if there are any complex carbohydrates, so complex carbohydrates will be converted into simple carbohydrates. Or simple organics, short, organics with a lower molecular weight. Okay. So coming to acidogenesis. So in acidogenesis, whatever we had in this, the simple carbohydrates or smaller organics, they will be converted into fatty acids. Organic and volatile fatty acids. And then the next step is acetogenesis.
Where is the use this process acidification?
Where is it? Can you repeat the question?
Where is the use acidification process this process?
See, this is a part of anaerobic digestion, right? So we were just discussing how anaerobic digestion is used for sludge digestion. So we just saw how aerobic digestion takes place, and then we discussed about anaerobic digestion. So these are the steps, or these are the sequence of processes which happens during anaerobic digestion. So as soon as you put sludge in anaerobic conditions, it is going to undergo hydrolysis. And after hydrolysis, it is going to undergo acidogenesis. So once acidogenesis gets completed, then it will go to acetogenesis. So it is a linear process. So first we have hydrolysis. So this is step number 1. Step 2 is acidogenesis. Step 3 is acetogenesis. And step 4 is methanogenesis. So it is a sequence of processes and individually it has no value. So I'm just explaining the various stages of anaerobic digestion. So now whatever acids were there in the second stage, so they will be converted into acetic acid, hydrogen and carbon dioxide. So there are specialized bacteria for each of these stages. Like for hydrolysis, we have hydrolytic bacteria, and then we have acidogenic bacteria, and then acetogenic bacteria, and then for the final stage, we also have methanogenic bacteria. So methanogenesis. So in methanogenesis, methane is generated by methanogenic bacteria. So there is a type of methanogenesis here. It is called acetoclastic methanogens. It is a type of bacteria. So this bacteria will split acetic acid into methane and carbon dioxide. So these are the 4 stages, and then we have different types of digesters. First being standard rate digester. So standard rate digester means there is no mixing. The process goes on for several days, and because it is done for us for several days without any mixing, there will be layers. So the scum layer forms at the top, and the supernatant or released water layer will be there below, and so on. And then there is the high rate digester. So for this we need to supply heat, and we also have to give mixing. And then the third type is a two-stage digester. So here in the first stage there is a high rate digestion with heating and mixing, and in the second stage we have the standard rate digester. So it is a combination of two different digester processes. So that's why it's called two-stage digester. Okay, now let's see sludge dewatering in detail. So sludge dewatering, like I mentioned, it's done with the help of sludge drying beds. So a sludge drying bed typically is made up of gravel and sand. So on top of this, the sludge is applied, and whatever liquids are there, they will percolate through the sand layer or gravel layer. So here, basically it undergoes filtration. Whatever water is there in the sludge, it will get filtered through the pores of the gravel and sand. So it's actually a multi-layer. So at the bottom you have sand, and on the top you have gravel. So water will first percolate through the gravel layer and come to the sand layer. And on top we have the solids, sludge solids. So whatever solids are there will be left over at the top. Water will come down, and with time it will also, some of the leftover water at the top will also evaporate. So we will be left with completely dry sludge solids. But this process is done in the open, under the sun. So if there is no sun or if there is rain, then this process cannot be done. So that is the disadvantage of this process. It won't work during the rainy season. So there are different types of sludge drying beds. The first one being unplanted. So an unplanted drying bed is just like how I showed you. There is a simple layer of gravel and sand, and on top we put the sludge and allow it to dry and allow the water to percolate through it. So with time we have to remove this layer of sludge. So we need to desludge it. Removal is also called desludging. So we have to remove this layer of sludge from the top after some time, because if this keeps adding up, then it will block the pores. So if we put on sludge at the top, then after a while water will not be able to flow through. So that's why we need to desludge regularly. But in a planted setup, it's like there is a layer of gravel and sand below. But instead of leaving it plain, we put the sludge here and we allow plants to grow on top. So imagine there is a sludge bed here. So there is sludge and plants are allowed to grow. So this helps in both ways. So on one side, sludge is allowed to dry and water is allowed to percolate. At the same time, the plant can get its nutrients from the sludge. So whatever minerals are required, we can get that from the sludge. So this is similar to a constructed wetland. So constructed wetland is a type of treatment using plants. So we allow the plants to grow, and as the plants grow, they take up the minerals, and it helps in both ways. On one side, there is biodegradation that's happening. On the other side, the organics are taken up by the plants and allow their growth. So in case there are pollutants present in the sludge, they will also be taken up by the plants. Like for example, there are heavy metals or there are some contaminants, then all of that can be removed from the soil using the plants. So that's the use of a constructed wetland. Okay, so do you have any questions so far? So if you don't have questions, then shall we solve some numerical problems? I need some response, guys. Someone has sent me a thumbs up. What about the rest of you? Okay, so question 1. So there is a city with a population of 3 lakhs. Okay, and it is generating sludge .09 kilograms of dry solids per capita per day. And the second one is the concentration of the sludge or the solids in the sludge is only 4%. And the volatile solids content is 65%. So of this 4%, only 65% is volatile solids. And the volatile solids destroyed is 45%. And the detention time is 15 days. And then the oxygen transfer efficiency is about 15%. Now you've been asked to find how much dry solids per day. How much of dry solids are generated per day, and what is the digester volume? Oxygen requirement, and the air volume required in meter cube per hour. Okay, so the first step is to find out how much of dry solids are generated per day. So solution. So before we find out how much dry solids are there, so we know that the city's population is 3 lakhs. So and they've also given us that the sludge generated is 0.09 kg per capita per day. So what this means is, for each and every person in this city is generating 0.09 kilograms of dry solids per day. So if every person is contributing 0.09 kg, and if there are if the population is 3 lakhs, then the dry solids should be 3 lakhs multiplied by 0.09. Isn't that right? So what will be this value? If you multiply and tell me what is 3 lakhs multiplied by 0.09.
27,000.
So it is 2 lakhs 70,000 kg of dry solids per day. So we solve the first part. Second part is the digester volume. So if we have to find out how much volume of digester is required, before that we need to find out how much sludge or what's the volume of the sludge which is generated. So we know that the concentration of the sludge is 4%, meaning there is only 4% of solids and the remaining is water. So as you know, before we first have to find out how much volume of sludge is required before calculating how much of digester volume is needed. So sludge volume is also the volume of solids, and we know that the dry solids weight is 2,70,000. So if we want to find out how much overall sludge is there along with the liquid, then we have to divide it by 4%. So sludge volume is the weight of solids divided by the percentage of solids. So what is the weight of solids here? We've already solved in the first part. So this 2,70,000 divided by what is the percentage of solids? Yeah. So 4% is 4 by 100, which is 0.04. So we write 0.04 here. And what is this number? What is 2.7 lakhs divided by 0.04?
675,000.
Right. And the units are in kilograms. So assuming the density or the specific gravity equals to 1, so if specific gravity equals 1, then we just have to divide this number by 1 to get the volume. So this will be the same as assuming the specific gravity is 1, so we have to divide it with the density. So density will be, density of water is 1000 kg per meter cube. So dividing this by 1000, this will be how much?
675.
And unit will be meter cube. So per day we need 675 meter cube. So that's the sludge volume generated per day. And now coming to digester volume. So we know how much sludge is there. So accordingly we have to decide the digester volume. So at least we need 675 meter cube every day. And our detention time according to the question is, this is 18 days. So the detention time is 18 days. So if every day we are getting 675 meter cube, then how much volume is required for 18 days? Can you tell me the volume required for 18 days? So every day you need 675 meter cube. For 18 days, how much will be required? How much will be generated? Huh? 12150 meter cube. So for 18 days, 12150 meter cube of sludge volume will be generated. So that is also the digester volume which is required. Okay, now the next part is oxygen requirement. So before we see how much oxygen is required for the digester, first we have to find out how much volatile solids are there. So according to the question, volatile solids are 65%. So of the total solids, total dry solids is 27,000 kg per day. So 65% of this will be 17550. So this is the mass of volatile solids. And you also there are some volatile solids which are destroyed in the process. So this is the total volatile solids which is entering the digester. After digestion, we have to see how much solids are destroyed or how much solids are degraded by the bacteria. So that according to the question, 45% of the volatile solids are destroyed. So it is given here. 45% of the volatile solids are degraded during the digestion process. So mass of solids which are degraded is 17,550 multiplied by 0.45. So 45% of the initial volatile solids are degraded. So how much is this value?
Seven 97.5.
7897.5 kilograms. Now, let's assume that the oxygen requirement is 1.5 kg of oxygen required per kg of volatile solids destroyed. So now tell me how much oxygen is required. So for every kilogram of volatile solids destroyed, we need 1.5 kg of oxygen. Then how much oxygen is required? First, how will you find out this number? 7897.5 multiplied by 1.5 is 11846.25. So this much kilograms of oxygen is required per day. Now this is given in terms of kilograms of oxygen, but usually we will take in terms of volume. So because we need oxygen to flow, so we have to calculate the flow rate of oxygen. And also so assuming 21% of oxygen is present in air, and the density of oxygen or the density of air is 1.201 kilograms per meter cube. So the air requirement, so we are not supplying pure oxygen, instead we are supplying air. So air contains 21% oxygen. So accordingly, we need to find out how much air supply is required to maintain this much kg of oxygen per day. So it is 11846.25 divided by, so 21% is 0.21. So 0.21 multiplied by 1.201. So how much is this number?
5641
5 6. Can you repeat?
56410.71.
0.71. Um, no, I think the answer is 46971.65, and it is in meter cube per day. So converting this to meter cube per hour, so we have to divide this by 24, and 46971.65 divided by 24. How much is this?
One nine five seven point one five.
Close. So it is 195 or 1949.5.
1957.15.
So it's close to 1950. And next we have to design the tank. So we know how much volume of uh, sludge digester is required, but we still have to find out the dimensions or the size of the tank. So here we make an assumption that the tank height equals 6 meters, and we also assume that it is a circular tank. So if it is a circular tank, then the formula for volume will be pi by 4 into d square into height. So d square is the diameter square. So this is equal to 12150. So height is 6 meters. So 12150 equals pi by 4 into d square. So find out d. What will be the diameter of d? What is d? I've given you the formula to calculate. You just have to tell me how much is the diameter. It's a simple equation, right? You just have to cross multiply and tell me. Okay, so in case you want to solve it later, I'm giving you the answer now. So it is about 50.79 meters. That is the diameter. And like I already said, we are assuming that the tank height is 6 meters, but we also have to provide 2 meter extra as free board. So total height becomes 6 plus 2, 8 meters. Okay, so we've solved this problem. So in case you want to try out, you can definitely do that. So do you have any doubts? Did everyone understand the problem?
Ma'am, in O2 requirement, oxygen requirement, why we divide by 24?
We didn't divide by 24, right? It's 21%. So why we do that is we are not supplying oxygen gas directly because it is expensive. So what we do is we supply air. So air has 21% oxygen, right? So yeah, so air has 21% oxygen, and if you want to get how much air is needed so that your oxygen content is 11846.25 kg. So I'll write it down here. So the O2 percentage is 21% in air. And oxygen required is 11846.25. So so if air is present, so air has 21% oxygen. So 11846.25 into 21 by 100. So air, mass of air into 21 by 100 should be this number. Are you understanding this?
Yes, ma'am.
Yeah, mass of air into 21% is 11846.25. So we need to find how much mass of air is there. So what will you do? You will bring this to the denominator, right? 11846.25 divided by 21 by 100. That's what we have done. So this will be how much? So we will be needing 56,410 kg of air. Now, we generally don't measure the weight of air, we instead measure the volume. So generally for gases, volume is measured. So even at home, you would have seen your gas cylinder. It is, like whatever volume is there, it is expressed in liters. So generally we don't go for kilograms. So, and since we have to maintain a flow rate is in meter cube per unit time or volume per unit time. So that is why it is always better to convert the mass of air into volume of air. So if we have to convert mass into volume, we have to know the density. So density of air is, just assuming, so the density of air is 1.201 kg per meter cube. So every kg of air will occupy, every meter cube of air will be weighing 1.201 kgs. So, and as you know, density is mass of air divided by the volume of air. Now mass is already you know it is 56,410. Now you have to find volume of air, and density is also something you already know. So volume will be how much? 56,410 divided by 1.201. How much is this? This 49,969.78. This is what we got here. Number is slightly different, but more or less it's the same value. So instead of going for two different steps, I've just divided the percentage of oxygen and the density of air at the same step to simplify things. So that's what we've done. Is it clear?
Yes, ma'am.
Okay, so if there are no further questions, then we will end the session here.
Okay, ma'am.
Okay. Okay then. Thank you all for joining.
Thank you, ma'am.
Thank you, ma'am.
Thank you. Bye, ma'am.
Bye.
Bye, ma'am.